So in this video we're going to talk about the equations required for plane kinetics of rigid body questions. So just quickly breaking this title down, when we talk about plane, what we mean is 2D. So we're only going to be looking at 2D questions. At the end here we have rigid bodies, and when we talk about rigid bodies we're talking about ones that don't deform when forces are applied. So another way of saying that would be that the shape doesn't change. Alright, and the final part is probably the main bit. So what we're talking about with this kinetics section is relating together forces and accelerations. Alright, so there's two types of accelerations that we're going to be trying to put on our rigid bodies. So one type is translational. Right, and that means that your body is moving in a straight line, or basically that. The other option we have is the rotational motion. So that's when it starts to rotate about its center of gravity. Alright, so with each of these questions, what we want to do is start with a free body diagram, which we can then use to relate together forces with a kinetic diagram on which we put all the accelerations. So as a general example, if we draw a free body diagram where this is our random body, we know it has a center of gravity at G, and if we have a whole host of different forces applied to it, so let's call them F1, F2, F3, F4, what we want to be able to do is relate them to the accelerations, and we do that by equating our free body diagram to a kinetic diagram, which should have the same body, which has the same center of gravity because the shape does not change. On this diagram we want to put accelerations. So if you sum together all the forces that are applied to your body, what we can do is equate them to the mass times acceleration through the center of that body. So that's the same as saying sum of forces is equal to ma. And this time we have a little bar that sits on top of the acceleration, and that's referring to the fact that that acceleration acts through the center of gravity. We need to be specific in these questions because we're also going to have the rotational component, which is going to mean that the whole body is not going to be accelerating linearly at the same rate. So the angular acceleration is related to, I'm going to put this as I bar alpha. Okay, so if you sum your moments about your center of gravity G on this diagram, remember that your moment is equal to the force multiplied by the perpendicular distance to G in this case. We know that it's going to be equivalent to, So if we sum our moments about point G, we know that it's going to be equivalent to this term here, which is I bar alpha. Okay, so what we end up with is our translational motion being this A bar term, and our rotational motion being related to this alpha term. So let's talk a little bit about what this I bar value in here represents. So all it is the mass moment of inertia, and when it has the little bar on top of it, it means that it's about the point G, or the center of gravity. Okay, so in context all it means is it's kind of like a geometric property that describes how the mass is distributed about the point G, and it relates it to then how easily our object is then able to turn. So that's kind of how you can think about this I bar property. So the units are kilograms meters squared typically. Of course you can have prefixes on top of that, and you should be able to look up the value in tables. So some people have obviously gone to the effort of deriving the equations for I bar for a bunch of different common shapes, and you should just be able to read them off. So down here I've put in a random table that I took off the internet, which gives you the value of I for several different common scenarios. The main one, honestly, that we're going to be working with is just this one on the left here, I guess these two cases, where we have thin bars. So I for a thin bar about its center of gravity is 1 on 12 ml squared. Alternatively, you can work out these I values about other points that don't represent the center of gravity. So in this example, they've worked out I about the end of the rod. You get obviously slightly different values for that then. Again, you can just look them up in tables. So I'll leave that there and come back up. So for these questions, what we end up wanting to do is, again, relate together the forces applied to the free body diagram and the accelerations on the kinetic diagram. And in effect, we kind of end up with some governing equations, and this is one kind of representation of them. So we can make it a little bit more specific if we want to, since this is kind of a general sum of forces equals mass times acceleration. Obviously, we can change that up into directions. And then we can also look at summing moments about points other than the center of gravity at G. So the first equation that I'm going to talk about is the sum of the forces, and we can split that up into x and y directions. So in the x direction, sum of the forces in x is equal to the mass times the acceleration in x, and again the bar is here to specifically say we're talking about putting that through the center of gravity. The equivalent for the y direction is this here. Okay, we're only going to be talking about 2D questions, so we're not going to have sum of forces in the z direction because we're not considering it. So the other governing equation is the moment one, and we already discussed what it looks like when you sum about the center of gravity. It becomes I bar alpha. But we can have some other ones. So what happens if we wanted to sum about some random point on our body? So let's call that point P. So the equation becomes I alpha, but then you have this extra part, which is MAD. Okay, so in this case, P represents an arbitrary point. Okay, so I bar is the same as back here, it's just your value about the center of gravity. Alpha is the angular acceleration, but here we have the mass times acceleration, that's the linear acceleration, and it gets multiplied by the distance d. So let's pretend that point P sits up here, and that's the one we're interested in summing about for whatever reason. The distance d would be, it's just like moments, you need to take the perpendicular distance between the acceleration's kind of line of action and point P up here. So this is like a perpendicular distance which sits in here, it's a right angle. Okay, so that's what that represents. You have one other option for summing your moments, and that's if you sum about a fixed point, which we'll call O. And the equation for that becomes sum of the moments about point O is equal to IO times alpha. Okay, so what changes here is that you need to calculate your I value about that fixed point, and again you should be able to look this up in a table for the equation. So that's your three governing equations, and I guess we should note that if you end up with more than 3 unknowns in your system, your rigid body system, unfortunately, obviously those 3 equations are not going to be enough for you to solve it simultaneously. So this often happens when you have constrained motion, and that's when you need to look for some other relationships that you can develop with your unknowns. So that tends to be if you have a bar that's constrained, for example, in 2 slots, the acceleration of one end of that bar is going to be related to the acceleration of the other end of the bar, because their motion is constrained in a slot, and the bar is a rigid body. So that's where you can kind of start to look for other equations. But otherwise, if you have simple questions, these 3 equations should be enough for you to solve.